Good day, students. In this tutorial, we're going to be going over how to find the vertical and horizontal asymptotes of functions and how to express our results using the limits definition for asymptotes. All right, so to get started, let's go ahead and write down what the limit definition for asymptotes are. Then we'll apply our definitions to two examples. All right, so we start with the horizontal asymptote. um, Horizontal asymptote. So the limit definition for the horizontal asymptotes is as follows. If the horizontal line y equals a is a horizontal asymptote, if it is a horizontal asymptote, then um, the limit of the limit as x approaches infinity of the function is equal to a, or the limit as x approaches negative infinity of the function is equal to a. Okay, so either the going to infinity or negative infinity, if you get the value a as the limit of the function, then that value is your horizontal asymptote, that finite value there. All right, so for vertical asymptotes, what is the limit definition? Vertical asymptote. If the vertical line x equals a, well, let's use a different letter this time. How about we use b so we don't confuse it with the horizontal? So if you have the vertical line x equals b, if this is a vertical asymptote, the vertical asymptote, then the limit as x approaches that value from the right plus of some function f of x is going to be plus or minus infinity, or the limit as x approaches that value from the left of some function f of x is equal to plus or minus infinity. Okay, so these are the two definitions of limits that we're going to be, limits definition of asymptotes that we're going to be using to conclude our problem solving process in the upcoming example. All right, so before we take a look at an example, let's look at the visualization here, just a graphical representation of these two limit definition of asymptotes. This right here is, let's say it's a x value, x equals b, so this is b right here. And then this is a y value, f of x equals a right here. So if you're approaching, this is approaching b from the left, and then this is approaching b from the right. Down here, we know that the functional value down here is negative infinity, way at the bottom of the y-axis, and way at the top of the y-axis is infinity. And then this is x going to infinity, and then x going to negative infinity. So for the horizontal asymptote, this horizontal line right here, what do you know? How is the function behaving as you get as x approaches infinity? As x approaches infinity, you notice that the function is approaching this horizontal line x equals a. All right, so a function is approaching a constant value as it approaches plus or minus infinity. That is your horizontal asymptote. Let me call it HA, just for short. And then now look at this vertical asymptote right here. What do you notice the function is doing as it gets arbitrarily close to this b value of x? As it gets really close to this b value of x, it tends towards infinity when you're approaching from the left and negative infinity when you're approaching from the right. So that makes this line right here a vertical asymptote. Okay, so this is what these two limit definition of asymptotes is saying. Okay. All right, so let's consider an example, concrete example. It says find the vertical and horizontal asymptotes of the given function. State your results using the limit definition of asymptotes. So let's say we have the following example. Say we have f of x is equal to x to the third plus 2 divided by 2x to the third minus 4x. Alright, so if you want to find, let's find the horizontal asymptote first. Horizontal asymptote. So what the horizontal asymptote is asking you to do is to say what the function is approaching as x approaches infinity or negative infinity. Okay, so for the horizontal asymptote, we're going to find the limit as x approaches, we'll do infinity first and then negative infinity afterwards. So limit as x approaches infinity of x to the third plus 2 divided by 2x to the third minus 4x. Now when you're taking the limit as x approaches infinity, if you're dealing with two polynomial functions, you can focus on the terms with the biggest degrees, since those are the terms that grow quickest as x tends towards infinity. In this expression right here, x to the third is the quickest in the numerator, so we're going to take the limit as x approaches infinity of x to the third. C2 is a constant, it doesn't even grow at all. In the denominator, these two terms grow, but this grows much quicker than that, so at infinity this is of no consequence. All that is relevant is 2x to the third. So this is the limit that this one can be reduced to when you're looking at x going to infinity. Now if you reduce this, you are going to have the limit as x approaches infinity of 1 over 2. Alright, so this constant value is independent of the direction of x. So our final answer is 1/2 as our horizontal asymptote. Okay? And then how about the limit as x approaches negative infinity of the function? Let's see. Some functions, the horizontal asymptote in both directions are the same. Sometimes you have a horizontal asymptote in one direction. In other cases, you have two different horizontal asymptotes going to the left and to the right. In this case, let's see what happens. This reduces to the limit as x approaches negative infinity. The quickest going on the top is x to the third. The quickest going on the bottom is 2x to the third. These two divide out again, so we have the limit as x approaches negative infinity of 1/2 and is also 1/2. So we have the same horizontal asymptote when you're going to infinity or negative infinity. Okay, so what's our answer? Our y equals 1/2 is a horizontal asymptote. The horizontal asymptote. Now what was our definition again? Since the limit as x approaches, in this case plus or minus infinity, we can condense them into one because they have the same limiting values. So the limit as x approaches plus or minus infinity of x to the third plus 2 over 2x to the third minus 4x. Both limits as x approaches infinity is equal to 1/2. So based on the limit definition of an asymptote, y equals 1/2 is a horizontal asymptote for this function. Alright, so let's box our answer and go ahead and look for the vertical asymptotes. So the second part of the problem, we have to find the vertical asymptotes. So let's write that down. Vertical asymptotes. Alright, so how do you find the vertical asymptotes? We're looking for points where we have an infinite discontinuity. So we have to take out any removable discontinuities from the function. So the original function is f of x equals x to the third plus 2 divided by 2x to the third minus 4x. So to find and cancel out the removable discontinuities, we just have to factor the numerator and the denominator and take out any common factors. The numerator is prime, so we'll leave it alone, x to the third plus 2. If we factor the denominator, we can take out a 2x, and we're left with x squared minus 2. And that can be factored further x to the third plus 2. It can be factored into, let's see, it can be factored into 2x times x minus root 2 times x plus root 2, just basically using the difference of squares factorization formula. Okay, so if you notice, we do not have any removable discontinuities here, nothing common in the numerator and the denominator that can be cancelled out. So now any x value that makes the denominator 0 will be an infinite discontinuity or a vertical asymptote. Alright, so to find our vertical asymptotes, we just take the factors in the denominator, set them to 0, solve for x, and those will be my vertical asymptotes. Okay, so from the first one, just divide both sides by 2, x equals 0 is your first vertical asymptotes. This one, add root 2 to both sides, x equals root 2 is a vertical asymptote, and then lastly, x equals negative root 2 is a vertical asymptote. Okay, so let's, using the limit definition of asymptotes, how can we state for certainty that these are vertical asymptotes? Now, so what we have to do, remember the definition of vertical asymptote using limits. If you approach from the left or the right of that vertical asymptote value, if you approach negative, if your function approaches positive or negative infinity for any directional limit, that value that you're approaching is a vertical asymptote. Okay, so we can just choose to approach these values from any direction that we want. Okay, approaching them from one direction and getting infinity or negative infinity is sufficient for us to conclude that they are in fact vertical asymptotes. So what I'm going to do is I'm going to take the limit as x approaches 0 from the right, and then let's figure that out. Basically, I'm going to approach all these values from the right. Okay, so the limit as x approaches 0 from the right of x to the third plus 2. If we get plus or minus infinity as our answer, then we can conclude that that this is in fact a vertical asymptote. Okay, so let me just take these factors from here, easier to work with. 2x times x squared minus 2. So let's evaluate this limit. I can plug in 0. 0 from the right, think of it as a small, extremely small positive number, the smallest positive number conceivable, like 0.000, like 0.0000000. You're getting really, really close to 0 from the right, okay? The smallest number conceivable. Another way you can think of it, 0 from the right is basically 1 over infinity, okay? And 0 from the left is negative 1 over infinity. All right, so let's go ahead and plug this value in here. So we're going to have a very small positive number raised to the third power plus 2 divided by 2 times a very small positive number times a very small positive number squared minus 2. Okay, let's simplify this. We're going to have a very small positive number to the third power is still going to be a really, really small positive number, plus 2, divided by 2 times a really, really small positive number is going to give you a very small positive number, times a very small positive number squared is still a very small positive number, minus 2. Now, what happens when you add a really, really small number to 2? The smallest positive number conceivable. You just get 2, right? Because this number is of no consequence. That over 0, a very small positive number. Now what happens if you take a really, really small positive number and subtract 2? You end up with negative 2, okay? Because this is pointless. Anyway, so you have this. What can we do here? We can reduce. 2 goes here 1, 2 goes here 1. So we're going to have 1 over a very small positive number. Remember, I stated earlier that 0, a very small positive number, is like 1 over infinity, right? So this becomes 1 over infinity. and then if you multiply the numerator by the reciprocal, wait a minute, there's a minus here, so let's not forget that. This 2 is minus, so put the minus here. So if we multiply the numerator by the reciprocal of the denominator, we'll end up with negative infinity. Okay, so since we are approaching 0 from the right and ended up with negative infinity, that automatically tells us that 0 is a vertical asymptote. Okay, all right, now we're done with 0. We have verified that it is, in fact, a vertical asymptote by the definition. Now let's approach root 2. We're going to approach root 2 from the right. Okay, limit as x approaches root 2 from the right. Okay, I'm going to use the factored form, so it's easy for me to carry out my calculations. So we're going to have x to the third plus 2, that divided by 2x times x minus root 2 times x plus root 2. Alright, we're going to find the limit, just making sure, as x approaches root 2 from the right of this entire expression right here. Okay, so let's go ahead and plug that in. We're going to have root 2 to the third plus 2. Alright, we're just going to substitute and evaluate over 2 times root 2 from the right. Alright, so let's put it right here. Really close to root 2 from the right times root 2 from the right minus root 2 times root 2 from the right plus root 2. Okay? Alright, we simplify this a little bit further. We're going to have this becomes 2 root 2 from the right plus 2 divided by, let's see what happens here. This is also 2 root 2 from the right. And then if you carry out this calculation, you end up with a very small positive number. Okay? And then you can also add this as 2 root 2 from the right. Now what happens when you multiply all these values in the denominator? You're simply going to get a really small positive number. So this becomes 2 root 2 from the right plus 2 over, multiply all these together, a really small positive number. Okay? And then this can be written as 2 root 2 from the right plus 2 over 1 over infinity. And then your final, next to your final answer, you have 2 root 2 from the right plus 2 multiplied by infinity over 1, and your final answer is infinity. So we can see clearly that root 2 is a vertical asymptote since the function approaches infinity as x approaches root 2 from a specific direction, namely from the right direction. Okay? Remember, it could be the left or the right. One or the other is suffice to conclude that that value is a vertical asymptote. Alright, next we have to approach the next answer we got, which is negative root 2 from any direction. How about we approach it from the right direction also? Okay, so limit as x approaches negative root 2 from the right, okay, of the same function, x to the third plus 2 divided by 2x times x minus root 2 times x plus root 2. Alright, so we just simply plug in these values into our x's and then evaluate the resulting expression. So we'll just evaluate this function at negative root 2 from the right. So we're going to have negative root 2 from the right raised to the third power plus 2 in the numerator, and then in the denominator we'll have 2 times negative root 2 let's write that again. So it's clear. 2 times negative root 2 from the right times negative root 2 from the right minus root 2 times negative root 2 from the right plus root 2. Okay? In the numerator, if we expand negative root 2 from the right, if we raise it to the third power, we're basically going to have negative 2 root 2 from the right plus 2. And then in the denominator, if we multiply 2 times negative root 2 from the right, we are simply going to have negative 2 root 2 from the right. And then when you combine these two, negative root 2 from the right minus root 2, you are going to have negative root 2 from the right also. And then this right here, negative root 2 from the right plus 2 is you're gonna get 0 from the right. So let's go ahead and simplify this. We're gonna have the numerator is still negative 2 root 2 from the right plus 2. In the denominator, these two multiply together, they're going to become positive. Well, quick correction here, it's supposed to be negative 2 root 2 from the right. Okay? Alright, so what I just want to illustrate is these two, when you multiply them together, the minus becomes a plus. Okay? So you get a positive number, 2 times 2, which is 4. 4 times 2 is 8. You're going to have 8 from the right. And then multiply that by 0 from the right. Okay? You don't actually have to work this out, because when you're multiplying it by a very, very small positive number, this entire thing is going to become a very small positive number. Okay, so this becomes negative 2 root 2 from the right plus 2 divided by, in the denominator you have 0 from the right, a very small positive number. Okay, and then this becomes negative 2 root 2 from the right. Let's put that there. Negative 2 root 2 from the right plus 2 multiplied, well, it's divided by 1 over infinity first, so we don't get confused. Remember, it's a very small positive number, the same thing as 1 over infinity. And then now we just multiply the numerator, negative 2 root 2 from the right plus 2 by the reciprocal of the denominator, infinity. So what is this going to be? If you look at this number closely, in the numerator, negative 2 root 2 is bigger than, 2 root 2 is bigger than 2, right? So if you subtract negative 2 root 2, if you add 2 to negative 2 root 2, you're going to end up with a negative number, okay? So what happens when you multiply infinity by a negative number? So you're going to have a negative number, whatever that number is, times infinity. Your answer is going to be negative infinity, okay? So that automatically shows that negative root 2 is a vertical asymptote. So let's go ahead and write down our conclusion that these are vertical asymptotes using the limit definition of asymptotes. Okay, so x equals 0, negative root 2, and root 2 are vertical asymptotes, since, remember, just one direction is sufficient for us to draw a conclusion. All right, since the limit as x approaches 0 from the right of our function, what was the function again? X to the third plus 2 over 2x to the third minus 4x. I'm not sure, let me verify that that's what we had before. Yes, 2x to the third minus 4x, okay? Limit as x approaches 0 from the right of that is equal to, we had our answer was negative infinity. All right, and we also found out that the limit as x approaches negative root 2 from the right of the function 2x to the third minus 4x was negative infinity. And lastly, we also figured out that limit as x approaches root 2 from the right of the function was equal to, what was our answer? Infinity. Okay, so remember, if you approach infinity or negative infinity for those directional limits, that value you're approaching is a vertical asymptotes. Okay, so this basically is the conclusion of the second part of problem 1. So thanks so much for taking the time to watch this presentation, and please post a comments to let us know what you think about it. And do subscribe to our channel for updates to other cool clips such as this. More tutorials can be found on mathcoachserve.com/calculus. Thanks again for watching and have a wonderful day.